The first law of thermodynamics applies the conservation of energy principle to systems where heat transfer and doing work are the methods of transferring energy into and out of systems. We looked at the conservation of energy in a previous video, and it basically sums down to the notion that energy cannot be created from nothing. In other words, it can't just pop into existence, and energy cannot simply just disappear. Energy can, however, change its form. And we see this everywhere in daily life. For example, when you turn on the light, electrical energy is being converted into light and heat energy. We also see energy transformation during a fireworks display. The chemical energy within the molecules of the firework mixture get released and transformed into light, sound, and heat or thermal energy. So energy never disappears. It just gets transformed into some other form of energy. Now, energy can also be transferred into and out of a system. So what do I mean by this? Let's imagine we're working with a simple piston that has a volume of gas in its chamber. The amount of gas in this chamber doesn't change. In other words, this gas cannot escape from this chamber, and no extra gas or any other matter can enter this system. But the transfer of energy as work or heat is allowed. These types of systems are called closed systems. So there are two ways we can transfer energy into this gas, and therefore increase the gas's internal energy. And if we remember back to our previous lesson, we defined a substance's internal energy as the sum of the kinetic and potential energy of the system's atoms and molecules. One way we can transfer energy into this gas is by doing work on the gas, using the piston. So what does this mean? Well, if we apply a downward force on the piston and move the piston a distance of d into the chamber, we're going to do work on the gas. But the gas can also do work on the piston. In other words, if the gas expands, it can apply a force to the piston and push it in the opposite direction. So in this case, energy would be transferred away from the system. And this is because internal energy within the gas is being used to perform work on the piston. Now, the second way energy can be transferred in and out of this system is through heat transfer. Heat transfer occurs when there's a temperature difference between the outside environment and the system. And we explored this in a previous lesson. So we can summarize all this now with the first law of thermodynamics, which is the change in internal energy of a system equals the net heat transfer into the system minus the net work done by the system. So let's look more closely at this equation and see how it relates to our piston example. The change in internal energy of our gas depends on two things simultaneously. In other words, the net transfer of heat into our system and the net work done by the gas. If we have a net positive heat transfer, this means that the temperature in the surrounding environment is higher than that of the system. So there will be a net heat transfer into the system. If the net work done is positive, This means that there is a net work done by the system. In other words, the gas is doing work by expanding and pushing against the piston. But notice the negative sign in the equation. When work is done by the gas's internal energy is reducing, and this is because the gas's internal energy is being transferred into work. So you may also see the first law of thermodynamics written like this, where we have a plus sign instead of a minus sign between the heat and work. This is all down to whether we're focusing on the system doing work, in which case the system's internal energy will reduce, or whether we want to view the transfer of energy by work to be on the system, rather than being done by the system. If work is being done on the system, energy is being transferred to it. We've got an energy transferred to the system. So if you see the first law of thermodynamics written like this, it's all just down to what convention the book or course wants to use. So the change in internal energy within a system can come about through an exchange of heat, work, or some combination of the two. Let's say with our piston system, we have 150 joules of net heat transfer occurring out of the system. We also have 159 joules of work that's being done on the system by applying a downward force on the piston. In this situation, what is the change in internal energy of this system after this process is complete? Now we can use either of these formulas here, depending on what convention you want to use. But here we're going to use the first formula, where the work is being done by the system. So for this example, is our Q value of 150 joules going to be positive or negative when we insert it into our equation here? So because the heat is being transferred away from the system, we'd expect this to reduce the internal energy, and therefore our Q value would be negative. What about this work value of 159 joules? Will it be positive or negative in this example? And remember the convention we're using. Our first law considers work done by the system to be a positive value. Well, this work is being done on the system. So under our current convention, this has a negative value. So after summing this all together, the system gains 9 joules of extra energy in this process. And we're guessing 9 joules of extra energy because more net work is being done on the gas than is being lost by heat transfer away from the system. So in our next example, we're heating up our system with a net heat transfer of 200 joules, and this is heating up the gas within our chamber. As the gas expands, it does 150 joules of net work on the piston. What is the change in internal energy in this system after this process? Well, now the net heat transfer is positive because we're transferring heat into the system. The work is also positive because according to the convention that we've chosen to use, we're focused on the work done by the gas rather than on the gas. Work done by the gas will have the effect of reducing the system's internal energy, and that's why we have a negative sign here. So in this case, the change in internal energy that we get for this example is a positive 50 joules. And this increase in internal energy would have an increase in the temperature of the gas and also the pressure in the chamber. In the next lesson, we're going to expand on the first law of thermodynamics by talking about simple heat engines. We're also going to talk about isobaric, isochoric, isothermal and adiabatic processes in thermodynamics, and how we can calculate the total work done in a cyclical thermodynamic process.